Welcome to this explainer. Today, we're unpacking what I like to call modern-day alchemy. We're going to look at how ordinary dirt, literally the exact same sand you'd walk on at the beach, is transformed into those sleek panels generating clean electricity on rooftops all over the world. It's something we see every single day, but the science happening inside them, well, it's nothing short of extraordinary. I mean, it sounds like science fiction, right? Turning a handful of sand into a literal powerhouse. But today, we're cutting right through the heavy jargon. We're going to dive directly into the data and the manufacturing workflows to see exactly how this incredible transformation happens. Here's our roadmap for today. We'll start with from sand to electricity and the photovoltaic effect. Move on to manufacturing, the epic journey. Break down the anatomy of a panel, and finally wrap up with types, efficiency, and lifespan.
All right, let's jump right into section 1, from sand to electricity and the photovoltaic effect.
Okay, let's answer the most burning question of all. How exactly does a solid, completely silent sheet of material magically create a usable electrical current? Well, the answer lies at the heart of every single panel. It's called the photovoltaic effect. This is a fascinating quantum phenomenon where certain materials literally release electrons when they get struck by light. You see, the vast majority of panels on the market are built from crystalline silicon, and what's really wild here is that this is the exact same base material used in your computer's microchips. Silicon is just absolutely perfectly suited to exploit this photovoltaic effect.
So, this brilliantly illustrates the atomic architecture. The silicon is treated with two very specific chemicals called dopants to create layers with opposite electrical charges. Notice that light blue upper layer? It's doped with phosphorus, which gives it extra free electrons, making it negative, or N-type. The darker lower layer is doped with boron, leaving it short of electrons and making it positive, or P-type. Where these two layers meet, an internal electric field is formed. This boundary is known as the p-n junction, and it is absolutely the engine of a solar cell.
And here is how that engine runs in 4 elegant steps, if we just follow the journey of a single electron. First up, sunlight, which is made of tiny packets of energy called photons, strikes the silicon. If a photon has enough energy, it literally knocks an electron loose from its atom, leaving behind a positively charged hole. Second, that internal electric field at the p-n junction immediately sweeps the freed electron toward the n-type layer and the hole toward the p-type layer. This perfectly separates the charges so they can't just recombine. Third, metal contacts collect these separated charges. And fourth, when connected to an external circuit, those electrons flow through a wire to get back to the holes. That flow of electrons, that is electric current. Amazingly, each individual cell produces roughly 0.5 to 0.6 volts of direct current. Just think about how many of those it takes working together just to power a single house.
But there is a catch. The electricity coming right out of the panel is direct current, or DC power. Now, your household appliances and the electrical grid, they run on alternating current, or AC. Because of this, the direct current produced by the sunlight has to pass through a device called an inverter. This seamlessly translates it into usable AC power for your everyday life.
Moving right along to section 2, manufacturing, the epic journey.
Now that we understand the really delicate atomic physics, let's talk scale. Turning raw dirt into a quantum-level power generator is no small feat. It is an epic 8-stage manufacturing flow that demands extreme temperatures and absolute chemical purity. It's honestly a true marvel of modern manufacturing.
It all begins by extracting silicon from quartz sand. This sand is heated with carbon in a submerged arc furnace at a staggering 1,900 degrees Celsius. To put that into perspective, that is literally hotter than volcanic lava. This yields about 99% pure silicon, but electronics need more. It goes through the Siemens process to achieve 6 nines purity. That's 99.99999% pure polysilicon. Next, this ultra-pure silicon is melted down again, and a massive, single cylindrical crystal ingot is slowly pulled from the melt. Finally, wire saws slice this ingot into wafers roughly 150 to 180 microns thick. That is basically as thin as a single sheet of paper.
Once we have those paper-thin wafers, the cell processing begins. They're chemically textured and doped with phosphorus to create that vital p-n junction we talked about. Then, an anti-reflective coating is applied. This is actually what gives solar cells their iconic blue color, which is a fun little fact you can spot next time you look at a roof. Then, metal contacts are printed right on them. Each finished cell is electrically tested and sorted by performance. For assembly, they are soldered into strings, laminated under heat and vacuum to seal out moisture, and fitted with an aluminum frame.
And right before leaving the factory, they undergo intense flash testing for power output and rigorous durability tests against wind, hail, and thermal cycling.
Which brings us to Section 3, Anatomy of a Panel.
By the end of manufacturing, all those fragile cells are built into a highly protective stack. Every single layer here has a specialized job, working together kind of like a fortress. On the very front, tempered glass lets light through while acting as a heavy-duty shield against impact. Right beneath that is an EVA encapsulant, which is a clear adhesive film that perfectly seals out moisture. Then you have the silicon cells themselves, connected by tin and silver-coated copper strips. Behind the cells is a polymer-based backsheet for intense weatherproofing and electrical insulation. Holding the whole shebang together is the rigid aluminum frame, and on the back, the junction box manages all the electrical output. Basically, it's built like a tank to survive decades outdoors.
And finally, Section 4, Types, Efficiency, and Lifespan.
Now, if you've ever looked closely at different solar installations, you've probably noticed they don't all look the exact same. The two most common silicon types you're going to encounter are monocrystalline and polycrystalline. Monocrystalline panels are cut from that single crystal ingot we mentioned earlier. They're highly efficient, have a sleek, uniform black appearance, and are typically the most expensive. Polycrystalline panels, on the other hand, well, they're cast from multiple silicon crystal fragments melted together. They have a distinctive speckled blue look and offer slightly lower efficiency, but generally come at a lower cost. So now you have the insider knowledge to instantly identify them when you're walking around your neighborhood.
Beyond standard silicon, there is also thin film technology. This completely skips those delicate silicon wafers entirely. Instead, thin film is made by depositing alternative photovoltaic materials, like cadmium telluride, directly onto lightweight substrates. Sure, this trades away some efficiency, but in exchange, the panels are much lighter and flexible. This makes them absolutely perfect for things like RV rooftops or curved architecture where heavy glass just wouldn't make sense.
When it comes to everyday performance for standard commercial silicon panels, they convert between 15 to 22% of all incoming sunlight directly into electricity. Now, I know that number might sound a bit modest at first glance, but in the realm of quantum physics, capturing that much usable power from ambient light is an incredible, highly optimized engineering feat. The remainder of that solar energy isn't wasted by some flaw in the system, it's simply lost naturally as heat and reflection.
And amazingly, manufacturers confidently warranty these panels to operate out in the harsh elements, baking in the relentless summer sun and freezing in the brutal winter snow for 25 to 30 years. Just think about that contrast for a second. Paper-thin silicon wafers engineered to survive decades of extreme weather. And over that massive timeline, the power output degrades by only a tiny fraction of a percent each year, commonly just 0.3 to 0.5% annually. That is some serious durability. So, the next time you see a solar panel gleaming on a roof or lined up in a massive solar farm, remember the epic journey it took. It started as raw sand, was blasted in furnaces hotter than lava, grown into perfect crystals, sliced paper thin, and engineered at the absolute atomic level just to catch a photon. It's a total triumph of science and manufacturing. Thank you so much for joining me on this explainer, but before we go, it leaves us with one final exciting question to ponder. If human engineering can turn everyday dirt into 3 decades of clean power today, what seemingly impossible leaps in energy await us tomorrow?